Having understood the LU decomposition for a square matrix, let's talk about the LU decomposition of a rectangular matrix under the assumption that we don't need row exchanges. First of all, let's set up a little bit about the size. Let's talk a little bit about the size of the matrices A, L, and U. So if we assume that A is m by n matrix, then L will be m by m, and U will also be m by n. This is important. So m, remember that m represents the number of rows in A. And the same is true for L and for U. So if you have 3 rows in A, then your L matrix will be a square matrix of size 3 by 3, whereas your U matrix will have the exact same shape as A. All right, now with this, let's write the elimination steps on A. So I'll copy A, 1, 3, negative 1, 2, 2, 6, 2, 6, 3, 9, 1, 8. Now the first pivot is this one in the first row. I eliminate underneath it. The operations are R2 minus 2R1 into R2 and R3 minus 3R1 into R3. The first row stays the same, of course. 1, 3, negative 1, 2, and then 0, 0. And this is 2 plus 2, so it would be a 4. 6 minus 4 is a 2. And the last row is 0, 0 again. 1 plus 3 is a 4. 8 minus 6 is a 2. So the last 2 rows are the same. Now, some of you may find this situation confusing. You see, in the second column, we don't have a pivot. There is nothing wrong with that picture. So the 4 in the second row will be a pivot. The condition for a pivot is that everything to the left of the pivot and under the pivot has to be, well, to the left and below of that left needs to be 0. So if we had a non-zero term in this position, then we would not call this 4 a pivot. We would have replaced the 2 rows and continued working. But since everything to the left of the 4 and under is 0, we can call that 4 the second pivot. So we continue the elimination steps. We have R3 minus R2 into R3, and we obtain the matrix U, 1, 3, negative 1, 2, 0, 0, 4, 2, 0, 0, 0, 0, with the 2 pivots, 1 and 4. So this is the matrix U. The fact that U has a 0 row, it says that the rows of A are linearly dependent. So the same relationship, well, we can sort of recover the relationship from the row operations, but that's not important right now. Or you could just simply observe that if you added the first 2 rows of A, you would get the third row. So there is that relationship. Now, let's find the matrix L. So just like in the square matrix case, you get L the exact same way. The first operation to be reversed would be R3 plus R2 into R3, and it acts on U, so it acts in the opposite direction. And then here we have R2 plus 2R1 into R2, R3 plus 3R1 into R3. Now, the last time in the previous example when we discovered L, we applied the operations in the reverse order onto the identity matrix and we got L. The same idea will work in this case as well. So you could start with the identity matrix, then first apply this operation and then apply these two operations. You could also just write L, and I'll show you how to do that. So L is a 3 by 3 matrix. Lower triangular means that everything above the diagonal is 0. So we know these three components. And what we have to do is figure out the three components, the three terms under the diagonal. So as I said, we are first going to apply this operation, right? Well, think about what was the purpose of the forward elimination step. The purpose was to eliminate what is underneath the second pivot. In the matrix L, that spot corresponds to the spot under the second pivot of L. So in there, I need to write the coefficient before R2, and since there is nothing, it means there is actually a 1 multiplying R2. So I have a 1 here. Then I go back to these steps. Their purpose was to eliminate under the first pivot, which in L corresponds to this space. And in there, I'm going to write the coefficients 2 and 3. And that's my L. So we kind of get L for granted right away. We know exactly what it is. And we can solve the system. So we have U, we have L, and A equals L times U. Now, from here, I want to ask a related question. And that question is as follows. So when we consider the system AX equals B, I want to ask what conditions on the components of B guarantee that AX equal to B will have a solution. Now, this is a very important question, and why do we ask it? We know that not all systems AX equals B will have solutions. When do they have a solution? Well, remember that A times X represents a combination of the columns of A. So you have this column and that column and that column and one more, I don't know, maybe purple. So we have these 4 columns of A, and we want to understand what kind of space their linear combinations represent. Well, this has to do with how many vectors in this collection of 4 vectors are linearly independent. The answer to that question lies in the number of pivots that the matrix U and the matrix A have. So I should mention here that the pivots of A are the pivots of U. You see, when you look at A, you cannot tell what its pivots are. Well, you could tell the first one, that's a 1, but you can't really tell whether it has 2 pivots or it has 3 pivots. Of course, it cannot have more than 3 because every row and every column cannot, every row cannot have more than 1 pivot. And every column cannot have more than 1 pivot. So since the number of rows is less than the number of columns, A can have at most 3 pivots. But it could also have just 1 or it could have 2. Well, when you look at U, you see that it has 2 pivots and they're located in the first and in the third column. This tells us that the second and the fourth columns of U are dependent. They depend on the first and the third. And the same relationship is true for A. You see, it's very easy to notice in U that the second row is 3 times the first row. And that same relationship is true in A. The second row is 3 times the first row. How could you tell the relationship between, or how the fourth row is a combination of the first and third. You see, the fourth row is not a multiple, the fourth column is not a multiple of a single column. It's actually a linear combination of those two. You have to add them up a certain way, and then you will get that combination. So what we can tell from the fact that A has two pivots is that the space of all linear combinations of the columns of A is just a plane. So when we ask this question, what conditions on the components of B guarantee that AX equal to B will have a solution, we are saying, how can we describe those vectors which are in the plane and not somewhere else? Because A times X represents a linear combination of the columns of A, and if we want AX to equal B, it means that B must also be a linear combination of the columns of A. Now, let's use the factorization that we have. So we have A equals L times U. If I replace L times U instead of A in the equation above, I have LUX equals B. Remember from the previous video, we called UX some C. So we have LC equals B and UX equals C. So we can tell if it's much easier to answer the related question for what conditions on the components of C guarantee that UX equal B will have a solution. Because when you look at U, you can see that you could produce any vector C. So I'll just maybe write a potential C. As long as it has, the first two components can be anything, but the third one has to be 0. So if I ask the related question, what conditions on the components of C guarantee that UX equal to C has a solution, it's enough to say, as long as C3 is 0, UX equal to C will have a solution. So we can use this for a related answer on B. Let's explore a little further. Let's actually solve this equation over here. LC equals B. We have the matrix L. I'll copy it again so I know it has ones along the diagonal, and then the coefficients were 2, 3, and 1. And this gives the following system. It says C1 must equal B1, 2C1 plus C2 equals B2, 3C1 plus C2 plus C3 equals B3. Now let me express the C's through the B's. So I know that C1 equals B1. All right, C1 is B1. So I can replace B1 for C1 in the second equation and in the third equation. From the second equation, I can write C2 as B2 minus 2B1. Now I can replace that instead of C2, so that's B2 minus 2B1. And then from the third equation, I get C3 equals B3 minus 3B1 minus, in brackets, B2 minus 2B1. And if I simplify that a little bit, grouping B1 with B1, I get B3 minus B2 and then minus B1. So I have this expression for C with components C1, C2, C3, which is equal to B1, B2 minus 2B1, and then B3 minus B2 minus B1. Now, AX equals B has a solution if and only if, that's why I write a double F here, UX equals C has a solution. The if and only if condition says that I can go in both directions. If ax equals b has a solution, then ux equals to c has a solution, and vice versa. If ux equals c has a solution, then ax equals b has a solution. Now remember, because a u has the last row equal to 0, I know that any combination of the columns of u must have 0 in the third component. So I know that my condition for solution is that C3 must be 0. That forces a relationship on B, which says B3 minus B2 minus B1 must be 0. So if the components of the vector B satisfy this relationship, then ax equal to b will have that solution. Let's go for a moment in the matrix A, and if you remember, I wrote here, if you write the three rows, R1, R2, R3, it is true that the rows satisfy R1 plus R2 equals R3, which is the same as saying R3 minus R2 minus R1 equals 0. So that relationship makes sense, but it's not always easy to see it. So we have to have methods to solve these problems. And that's enough for today.